So, today I am going to introduce the crystal operators on words. It is very similar to what is done on paths. In fact, it is quite a bit simpler because we are restricting ourselves to paths that come from words. So, we are going to define some operators. So, we have word W equals A1, A2, AK in AN, and we are going to define operators EI, FI. Yeah, thanks. So, we are going to define three operators EI, FI and sigma I from AN star to AN star disjoint union, a special symbol which we will call 0. So, this is the case when the crystal operator cannot be applied, so to speak. And the way it is defined is, well, it is an algorithm. So, what you do is, at every stage of this algorithm, you will have a part of the word that is frozen. Once a part of the word is frozen, you do not touch it anymore, but it just stays there as it is. And you freeze, and then at some point you are left with a special kind of segment, you do a transformation, and then that is your operation. Okay. So, let me just explain this. So, let me give you the algorithm. So, scan the word first. Okay. So, first freeze. So, I am going to define this. Let us fix I firstly. Okay, so, I will define it for each I, and this I goes from 1 to n minus 1. So, fix I. Now, freeze all letters not equal to, let us say j for convenience, instead of writing I plus 1 all the time, I will use the letter j to denote I plus 1. So, freeze all letters different from I and I plus 1. So, this is kind of like going from the path pi to the path, what do you call it, h I of pi. So, you kind of ignore the other letters, but it is not quite ignore, you freeze them, you keep them there, but you are not going to see them really in the algorithm. And then, so whenever you have frozen something, there is an unfrozen part. So, now we will only look at the unfrozen part. So, if the unfrozen part, or I should say while the unfrozen part of W is not of the form. So, this unfrozen part now is going to have only I's and I plus 1's. I raised to R, j raised to S. You do the following steps. Scan W from left to right, and then freeze every segment in the unfrozen part. Of the form 2 1. Okay, so you scan the word W, and every time you come across a 2 followed by a 1, there could be frozen stuff in between, but if a 2 is followed by a 1 with maybe, oh yeah, sorry, j and I, from j I. So, there could be stuff in between, which is frozen, but if a j is followed by some frozen stuff and then an I, then you freeze that j and I. Okay, and you repeat this until at some point eventually your word will be of the form I to the r j to the s. Okay. So, now what you have is you have a word. So, let me just do a running example over here. So, so let us just take a word with 3 letters. Okay. So, suppose I want to apply E1 to this, say let's just fix I equals 1. So, firstly I will just freeze right away all the things that are not equal to I and I plus 1. So, I must freeze everything that is not equal to 1 or 2. So, I will just draw the frozen part in this purple color. So, this is frozen now. So, now let us look at the unfrozen part. Maybe I will just underline it, that is more visible. So, now let us look at the unfrozen part, and I will scan it from right to left, and every time I see a segment of the form 2,1, I will freeze it. So, here is a segment of the form 2,1 and here is a segment of the form 2,1, and I have frozen it, and now I go back. Now, is the unfrozen part of the form a bunch of i's followed by a bunch of j's? Yes, it is, right. So, now here it is 1, 1, 2. It is quite possible that I might need to go through this process of scanning from left to right and freezing more than once, but in this case it stops after one step. So, now I have this unfrozen part which is 1, 1, 1, 2. Oh, 1, 1, 2, sorry, this one is not there. Yeah, I did not underline it well enough. Yeah. So, all this is frozen. Yeah. So, only this, this and this is remaining. And then so we'll so for EI, so so now replace the unfrozen part by, sorry, no, for all of them I am fixing I will define now for each of them what to do. So, replace the unfrozen part I to the R j to the S by, so there are 3 cases. So, for EI, for HI, FI sorry, and for sigma I. So, here it is I to the R j to the S, and so for EI you just replace it by I to the R plus 1 j to the S minus 1. For Fi you replace it by I to the R minus 1 j to the S minus 1, and for sigma I you replace it by I to the, you just interchange the R and S, I to the S j to the R. Yeah. So, now of course, there is a problem. If S is 0, then you cannot do this, right, and if R is 0, you cannot do this, and this you can always do. So, and EI W equals 0 if S equals 0, Fi W equals 0 if R equals 0. So, that is another condition, that if R is positive here, then you can apply Fi, right, but if R is not positive, then you can never do this R minus 1. So, you just set it to be 0. So, So, let us say with E I equal to 0, with F I equal to 0. So, let us just apply it here. So, what do we get? So, we get E 1 of W equals, so the unfrozen part remains the same 3, 2, 1, and then this frozen part for E I have to increase the I. And F 1 of W is 3, 2, 1, 1. So, this 1 has to become a 2. And for sigma I, sigma 1 of W, what happens? I had 1, 1, 2, I should make it 1, 2, 2, interchange the number of 1s and 2s. So, in this case, sigma 1 is the same as F 1. Now, if I try to apply E 1 again to this word, then I will get 0, because after you freeze, the frozen part actually remains the same, and there is this 1, 1, 1, there is no 2s, right. So, let us just do a few more examples. E I squared W equals 0. What about E 1 squared W? What about E 1 F 1 W? So, here I had 1, 1, 1 for E 1, the unfrozen part, right. So, I should change it to, oh whoops, there is a typo here, this should be S plus 1. So, if S is 0, I can definitely apply this, I will just introduce 1 F. So, this will go back to W, okay. So, that 1, 1, 2 became 1, 1, 1, and now when I apply, sorry, what do I mean? Yeah, and when I apply E 1 again, it becomes 1, 1, 2 once again, right. And sorry, no, it is still 1s followed by 2s, but the number of 1s and the number of 2s is swapped. Which one? So, here let us just do it more carefully, sigma 1 of W. So, the unfrozen part is 1, 1, 2. Okay, so, it has 2 1s and 1 2. So, I need to make it so it has 1 1 and 2 2. So, I will replace the unfrozen part by 1 2 2. Maybe it is easier in this case to underline the unfrozen part and see what is happening. So, this is the unfrozen part. I will put lines on top to show you what is the unfrozen part. And F 1 squared of W, what is that? So, this is F 1 W, it is 1 2 2. So, I can change it, I can change one more 1 to a 2, right. So, it is 3 2 1 2 2 1 3 2 2. So, this is the unfrozen part, and now the unfrozen part consists entirely of 2s. So, if I apply F 3 squared F 1 cubed W, then this will be 0. Okay, and if I apply F 1 E 1 W, again it will give me back W, because I have this 3 1s and then I put back 2. So, we have this I string through W. So, we have W, we have E 1 W, and then we have 0, and then we have F1W, sorry, what am I doing? E1W, F1W, F1 squared W, and then 0. Yeah, but I have labeled this by E1. Yeah, so we can also label it by F1, and if we start from here, then we could just say this thing F1, F1 squared, F1 cubed, and so on. So let's just make some observations. So I'll call the so I'll say delta I W E I. This is going to be the number of times I can apply E I to W. And similarly, so maybe I'll just say H, where H could be you can think of this as the it's I think it's sometimes called the EI, the H depth of W. Okay, how much EI can I apply to W? And if you look at this form, then this is in the algorithm after you have done your freezing business. This is how many times can I apply EI? Well, I have Sj's and I can reduce them to 0, right. So, this is equal to S. So, delta W E I in the notation of the algorithm is S, delta W F I is equal to R, right. And when we were freezing away stuff, we were always freezing one J and one I together, right. So, what can you say about this? Delta W E I minus delta W E j equals not E j F I. This is equal to S minus R, but this is also the number of J's in W minus the number of J's in I's in W, right. So, you can think of this as alpha I inner product with the weight vector of W. I thought the roots were in the dual space and the weights were. Oh, okay. Yeah, I would have called those co-weights anyway. I guess maybe I'm confused. Yeah. Okay. So whatever convention we've been using, and yeah. So let's and so then we define a crystal based on these things. So So given a word W, let should I call it B of W? B of W, that is bad, no, because for you W is the dominant word. So I will call it C of W. Denote the set of all words in A n star. So W in A n star. B of W is good because I am not insisting that W be dominant though. In A n star, that can be obtained from W by a sequence of operations E I F I goes from 1 to n minus 1. Now, this set comes with various relations. So, we have a relation corresponding to each E I. So, yeah, right, the number of j's minus the number of i's. So, the number of j's is the inner product of E I with W, the weight of W is what? So, weight vector of W, I am distinguishing it. Earlier I was saying weight for a monomial. By weight vector of W, maybe I should define it. I thought that it is perhaps implicitly clear, but let us just be careful. So, weight vector of W AK is the vector mu 1 mu n, where mu I is equal to the number of j such that Aj is equal to I. Okay, how many times each letter occurs in a word? So, it is a sequence of operators E I F I, this thing, and this has some additional structure. We think of it as a colored graph. So, endow BW with the structure of a directed colored graph. There is an edge from W of color I to W prime if F I W is equal to W prime. So, that is the definition of a crystal, and this coincides with whatever definition you have seen in the other cases when the paths are based on these words. Yeah, no, so this is just a string, but we could also apply, we have not even tried to apply F2 or E2 to this example. Yeah, yeah. And so, of course, this thing will change inside the thing. So, let us just make a few observations about what happens to the weight vector, right. So, let us call this, is there a notation for this weight vector in the, yeah. Endow. Endow means give. Like you give it, right? You yeah. 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 So add to it now. Right now, it's just a set. Give it more structure, and then with that structure, it's called a crystal. So when I say two crystals are isomorphic, I would say not only are those two sets bijective, there exists a bijection between those two sets, which preserves these directed edges and their labels. So that would be the crystal isomorphism, notion of crystal isomorphism. So I'll call this the weight of W, or maybe I'll just call it W of 1. How's that? Or is that too confusing? No, let's call it. Okay, I'll call it weight of W. And this is not to be confused with the V of W, which was the weight I of W. No, this thing is weight of W. Yeah, this thing. Right. So what happens if you do? So if you take weight of EIW, how does it differ from weight of W? It's weight of W and then so I'm asking what did I change, right? I'm only interested in how frequently the various letters occur. The frequencies of letters I and J change, right? And if I apply EI, then the frequency of I increases and the frequency of J decreases. So it is plus minus 1 in the ith place and plus 1 in the jth place. This vector is sometimes known as minus alpha I. So just since I didn't use it in this course, alpha I is the vector 0, 0, 0, 1 in the ith place, minus 1 in the jth place, and then 0, 0, 0. So you have these vectors for I equals 1 to n minus 1. And now what I am doing is I am increasing the number of i's. So it's plus alpha I. And what about weight of sigma IW? So this is SI of weight of W. It's a reflection. So this is a reflection perpendicular to the it's a reflection about the plane perpendicular to this vector alpha I. It just interchanges the I and J. Yeah. So yeah. Okay. So let's just do an example of a crystal. Sorry. Oh yeah, okay. I was wondering why suddenly I had earlier calculated with minus alpha and why did that change? But usually the root is the larger thing first and the So sorry, I think it's better as he says. Of course, it's not compulsory, but it's definitely better because most people do it that way. To do that, to put a minus here. Oh, this is still the same. So, when you say better, it is a euphemism, you mean it is wrong. Okay, let me just. No, that choice dictates this choice. There's only one choice. Yeah, this was okay. That's what I had earlier. So then this was also okay, right? Okay. He almost convinced me that it was not okay. Yeah. Ah. Yes, yes. So then this should be negative. There should be a negative here. Yeah, so maybe I should put F here and E here. So let's do, I think that's better. Yeah. So the mistake is over here, not over there. And then it's okay. In any case, that's the length of the string. So let's just take n equals 3, and let me start with a very simple word, something like 212. Okay, then let's see what all I can get from 212. So, so if I want to apply, okay, I should write down again, like I had written the Knuth rules in the corner, EI of I raised to R j raised to S is, I have already forgotten, what was it? I raised to R plus 1, j raised to S minus 1, Fi I raised to R j raised to S is I raised to R minus 1, j raised to S plus 1. Okay? So, so if I take this W, can I apply, so if I freeze, right, then I get this 2 1 freezes and I am just left with a 2. So, I can definitely apply an EI, but I cannot apply an Fi because there are no ones. So, I can apply an EI, but not an Fi. So, that means that it comes by applying an Fi to something, right. So, I will write it like this. And what is that word? 211. Okay, I should probably say this also, that EIW equals W prime and not 0, right. Then this is equivalent to, yeah, Fi of W prime equals W. So, these two, you can think of EI and Fi as they are not really functions, because sometimes they are not defined. So, one way of dealing with that is to introduce this new symbol 0 and make it a function from the domain, which is words, and the range, which is words union 0. The other way is to just think of them as relations. So, EI and Fi are relations, and so you are just saying that these two relations are inverses of each other, in the sense that W is related to W prime via EI, then W prime is related to W via.
So, the EI and their inverses, so long as the image is not stored.
Yeah.
So, if you do a graph using Fi for edges and you do a graph using EI for edges, you get different graphs.
The directions will be reversed.
But except for the ones that lead to 0.
The ones that giving 0 don't, there is no this thing. It's the same graph with the arrows reversed.
Those edges,
there will be, so that is what I am trying to clarify that issue. I am saying that think of E I and F I, it is better to think of E I and F I in my humble opinion as relations. Okay, so we will say that if E I W is W prime, then we will say W is related by a relation E I with W prime. Okay, and if F I W is W prime, we will say W F I W prime. So, you have these relations, one for each, you have relations E I, relations F I for I goes from 1 to n minus 1, and these relations are mutually inverse, in the sense you know what the inverse of a relation is this. Okay, it always exists. It's so these are really relations, not functions. So, that should clear up that confusion if you just think of them as relations. So, this edge is actually that relation. Okay, so here we found it convenient to apply F I, and so we draw an arrow backwards. Now, can we apply F I again, F 1, I should not say F I should say F 1. Okay, what other things can I apply to this? So, I have 6 options, right? E 1, F 1, E 2, F 2, oh no, I have only 4 options, right? N is 3. So, even though only the letters 1 and 2 occur here, I am living in a world where there are 3 letters. So maybe I can try to bring in a 3. So I found that I cannot apply, I could not apply F 1, but I could apply E 1. Let us look at whether we can apply F 2 or E 2. So, if you try to fix I equals 2 now and then you freeze, then that means you are just removing all words of the form, you are freezing all letters 1. So, then you are just left with 2 2. So, now I is 2 and j is 3. So, you can apply, you cannot apply E 2, right, but you can apply F 2. So, you get an edge out of here and it is 2 1 3, because 2 2 becomes 2 3, and you can again apply F 2 to 3 1 3, right. And what else can you apply? So, let us see. So, we are done with this, we have found all the neighbors of this node. You would freeze the 1, and so you are left with 2 2. Okay. Oh, sorry. So I have applied F 2 and F 2. So a 2 becomes a 3, but I cannot apply E 2 because there are no 3s to reduce. Okay, so we are done with all the neighbors of this guy. Let us see if this guy has any neighbors. Well, here also I can apply. So, if I freeze the 1s, then I will just have a 2. So, now I can apply F 2. Right, and so this would be a 2, and now okay. So here I can apply F 2, I cannot apply E 2, I cannot, I have already applied F 1, I cannot apply E 1. Because after freezing it is 1. 1, yeah. Right. Okay, so what else can I do here? What about this? Can I apply, what can I apply to this? So, if I freeze the 3, I have 2 1s, I can change them to 2s. So, that would mean that I am applying E1, right? I can apply E1 2 times. and maybe my directions are not chosen that well. So what else can I apply here? So if I take this and I freeze the 3's, then I can apply what? I have 2 1's, so I can apply F1 2 times, right? What? Not F1, yeah, F1. 3 1, oh, so wait. Yeah, I should have been applying it in this direction, right? So 3 1 2. If I apply F1, I would get 3 2 2. So it's yeah, I think I already did this, but I wrote it in the wrong place. So yeah, 3 1 2, and then 3 2 2. And I think now, okay, and so on. So you can try to draw the whole crystal. Maybe this is a good exercise for the tutorial. Oh, okay. So with these 3 letters, okay. Yeah, there's an interesting square in here, right? 2, 3, 4, 5, 6, 7. No, I'm missing just one more. Yeah. So what is that? 3 2 3 probably. And my guess is this. 1 2 2 1 2 1 1 2. That's what I remember. Yeah. Okay. Yeah. So yeah. So this is the crystal. Okay. So the standard example once again. Yeah, I think I saw it being done once. So. So in fact, Robinson's correspondence, remember? So how did this work? This was the Robinson-Shenstedt star correspondence, RS star. So then maybe this should be, yeah. We applied that and we got a dual tableau, and we also got a Yamanouchi word. How did we get the Yamanouchi word? We got a standard tableau, and from that standard tableau we had an algorithm to convert a standard tableau into a Yamanouchi word. So what we are going to see is that this correspondence can actually also be obtained from crystal operators. That this Yamanouchi word is basically going to be, you start with this word and then you keep applying f's. Apply all kinds of f's till you can no more apply any f's, and then you would have a Yamanouchi word. So you do dual insertion, but you will get a dual tableau as a word, but you can think of it as a semi-standard Young tableau, and it turns out to be the same as the insertion tableau. That tableau turns out to be the same as the insertion tableau of your word. So, yeah. But as a word, it's different, you see. So this is kind of the theme I want to. This is the thing I want to go towards. So firstly, here's a easy lemma. So y w belongs to a n star is a Yamanouchi word if and only if delta w f I equals 0 for all I. So in this crystal, where's the Yamanouchi word? It's this one. I could not apply, wait, what? Delta W E I equals 0 for all I. E I. Yeah. So I could not apply any E I to this word because, okay, so why is this the case? This is fairly straightforward. So when you say that a word is Yamanouchi, so firstly, then what you have is that for every suffix of this word, that means every you cut the word somewhere and look at everything to the right. So that's called a suffix. So every suffix of this word, the number of i's is at least as much as the number of I plus ones. So then if you are going to take this word and you are going to strike out all the pairs 2 1 2 1 2 1 or let us say j I j I j I, then after freezing all segments of the form j I, if you are left with I raised to r j raised to s, then this what must you have? You must have that r is greater than or equal to s. But then if you that means that this word is not Yamanouchi, because that would mean that if you are up to this point. So let me just how should I say it? Yeah. After freezing all after freezing everything, yeah. Yeah. So so if it's Yamanouchi, there cannot be any j left. So so if there is a j, then it cannot be Yamanouchi, and so I would have like I to the r, j to the s, and I couldn't have a 2 on this, j on this side and an I on this side in the frozen part, because that would then cancel this. So, then there is a bunch of paired up ji's on this side and a bunch of paired up ji's on this side. So, then if you look at any part of the word which involves, say, some of these j's and none of and the stuff to the right, then that will not have dominant weight. Okay. So, if it is Yamanouchi, then you cannot apply any Fi. And conversely, if you cannot apply any EI, and conversely, if you cannot apply any EI, then again what you will see is that after freezing you will never get any S surviving, which would mean that the thing. So, I will leave this maybe for the tutorial. So, okay. Now, what you can do is, and this word over here, this one is AntiYamanouchi, in the sense you cannot apply any FIs. Okay, so this is an equivalent characterization of Yamanouchi. So, here is another exercise. What words have, so give a different description of words which have delta WFI equals 0 for all I equals 1 to n minus 1. Okay, these are what I would call anti-Yamanouchi words. So, now what you can do is, you can start with any word, and then you can apply a sequence of, you can keep applying whatever f's apply to it. So, ease, apply all possible ease, apply. Okay, so I will give it as an algorithm. Start with the word W. So, what you do is, until, while there exists I in 1 to n minus 1 such that I can apply EI. You take W and replace it by EI raised to delta W EI of W for the least such I. Okay, and then you output W. Maybe I could have written a few more lines of code. I could have said take I going from 0 to n minus 1. If delta W EI is positive, then apply EI. So, maybe I should, yeah. One to n minus 1, not easy. So, what will happen now? This will return a word to which I cannot apply any EI, right. So, this is what Robinson, yeah, okay, let me write it more clearly. So, that's, so let me write down this algorithm of Robinson's. So, input W belongs to A n star. Then while W is not Yamanouchi. What you do is, for I goes from 1 to n minus 1, if delta W E I is positive, you replace W by E I W. Okay, and then after you after you run this loop, you again check if it's Yamanouchi or not. If it is Yamanouchi, then you return W. So, this is exactly the algorithm that Robinson gave. So, what this algorithm does is it takes a word W and returns a Yamanouchi word. So, this algorithm defines a function y from A n star to yam, set of all Yamanouchi words in A n star. So, if you take any of the words in this crystal, they will have this yam. And what we already saw was that that the Q star tableau of this Yamanouchi word is we have a description for that. Okay, so now let me try to relate this crystal business with the Robinson-Shenstedt correspondence. No. So, if you look at these words, so let's see what what is interesting here is that all these words are actually tableau. Let me redraw this diagram. These are all tableau words. So, far from it, right. So, it looks like the crystal operations take tableau to tableau. There is another crystal we can draw, which is I do not know if this example has also been done. So, now we would take words which are so is there a non-tableau word with weight 2 1, that is it has 2 1s and 1 2. Okay, so this is a Yamanouchi word with weight 2 comma 1, right. Is there another Yamanouchi word with weight 2 comma 1? 1 2 1, right. So, I can also take 1 2 1 and I can do the same thing there 1 2 1. and if I apply F1 to it, then presumably I get 1, 2, 2, right? And then if I apply F2 to it, then I will get 1, 2, 3, and then if I apply F2 to it, I will get 1, 3, 3, and then if I apply, hey, I am just kind of guessing these things. So 2 to 1. Oh, yeah, I freeze the 2, 1. Okay. Then this is all wrong after that. So then if I apply F2, then I will get 2, 3, 1, right? And then I apply F2, I will get 3, 3, 1, and then I will get 3, 3, 2. So this is 1, 2, 2, 1, and this is so if I am applying 2, I must freeze the 1, so I will get 1, 3, 1, and then I will get so now I must apply 1 again. So now I will get 1, 3, 2, and then I will apply 1 again, I will get 2, 3, 2, and then I will apply 2, and I will get 3, 3, 2. So here are 2 Yamanouchi words, right? And they both, so this one is already a tableau. What is the insertion tableau of this word? It is the same thing, right? Let us take something over here. What is the insertion tableau of this word? So I am taking 1, 3, and then the 2 bumps up the 3. So the insertion tableau of this word is indeed this thing, right? So what you are seeing is that you can take the tableau words and apply the crystal operations, you get a certain graph. Okay, if you want, you can write them out in terms of tableau themselves. And you take any other Yamanouchi word and you apply the crystal operations, you get an isomorphic graph, and what is more, each point in this isomorphic graph is determined by where it lies in that graph in terms of the tableau. Okay, so this is how, I hope I have been able to explain how these things are related. Okay, so of course it remains to prove all of this. So what we are saying is, well, tableau are words and then you can see the crystal operations on it. Yeah, you can. So I think, but you know, it amounts to the same thing. You kind of have to cancel off things and then you have to add. So if you look at the book of Stanton and White, they do it like that. But it's nothing different. It's the same thing. You just don't look at the word, you look at the tableau. But the thing to show is that if you start with the tableau and you apply a crystal operation, then you will still get a tableau. So once you know this isomorphism theorem, it's here's another way to get Robinson's correspondence. You have a word, right? No, I give you a tableau and a Yamanouchi word. Okay, so what you do is you draw the crystal for the tableau. Okay. And then you draw the crystal for this Yamanouchi word. You draw the two crystals, you find the guy in this crystal which corresponds to the tableau in that crystal, and that will be your word W. So that's, so let's do an example here. So suppose I am given, I have this mystery word W, and I am told that P star W is the tableau 132. Okay. And I am told that y of w is 1, 2, 1. Then do I know who w is? W is the word. Can you find it? No. 213 is just 132, right? It's the same thing. But the Yamanouchi word also matters. The Yamanouchi word is 121. So it's 231. This is your W. So it all looks like magic. So yeah. So there are a couple of things that need to be proved, technical things. Huh? Yeah. No, but they're. I mean, I'm referring to this picture, I guess. So, yeah, but you should write 213. Yeah, I'm writing. This is 213. Column word. Sorry for that confusion. So maybe I should have done this with, yeah. Huh? Yeah. So these pictures refer to column words, and this middle picture is agnostic as far as it comes to rows and columns, right? It's the column words. This could be 313, but okay, this would be 213. So here it's the same, but let's see. Yeah. So this one, for example, will be 131. Yeah. It's a bit, yeah, sorry. So when I write it like this, it's always, you know, if it's a P star, then you should take the column word. So there's that little problems. The column word is 213. No, the row word is also 213. Yeah. Okay, so yeah, where are my notes? Yeah, okay, so so one thing about the point is that this Q star tableau will not change for a word, or we'll use but I'll prove it with Q tableau. So let's just so theorem, if W is congruent to, so this is let me just stick to Rob. So this is the coming from RS star, but there's a similar bijection coming from RS. I'm more comfortable with that, so I'll stick to that. So here's the theorem: if W is congruent to W prime, then QW is equal to QW prime. Okay, and oh no, what am I saying? If W prime is equal to HW, then QW prime is Q of HW prime for H equals EI, Fi or sigma I. So, what we are saying is that these crystal operations, they do not change the Q. So, in other words, we said that all the words with the same Q form what is called a coplactic class. So, these let you be inside the same coplactic class. So, I won't give the complete proof. I will give you a proof in the simplified case where W consists of just 2 letters. No, I mean, but if you look at the crystal, then yes, it becomes if and only if. So, but right now I will just prove this. So let us just take for simplicity, we will take the case where n equals 2. So, then we are taking this word which has a bunch of 1s and a bunch of 2s, and we want to know whether Q of W is the same as Q of HW. So, so then the key thing is to find out the place where this. So, if you have say let's take also H equals maybe EI. So, what will happen is that you will have this word A1, A2, AK, and then there will be some place where you have this last one, and then you have yeah. So, EI, what does EI do? EI turns 2s into 1s, right? I is 1. So, you will have this first unfrozen 2, right. So, your word W will be of the form U 2 V, where this 2 is the leftmost unfrozen 2, and all the 2's to the left of this are frozen, and all the 1's to the right of this are frozen. And so, what does it mean about this? It means that to the left of this there are so you have cancelled off all pairs of the form 2 1, right. So, what does it mean? It means that to the left of this there are more 1's than there are 2's, right. So, U has, so U is so I want to say that U is actually Knuth equivalent to two to the K 1 to the L, where L is greater than or equal to K. So, Okay, so let me. No, there are more L's, there are more 1s on this side than there are 2s. And not only that, every one follows, is paired off with a 2 to its left. Every one here is paired off with a 2 to its left. Every 2 is followed by a 1, and then there are no more 1s left. There are no more 2s left. Every 2 is followed by a 1. Yeah. So every 2, okay. So is followed by a 1. So there are more 1s. Yeah. Every 2 is followed by a 1, and there are more 1s. So what happens is when you do the insertion here, at every stage, if you have a 2, you will have at least that many 1s, right? Which means that if you look at this P of u, then you will have 1, 1, 1, 1, 1, and then you will have some 2s, but fewer 2s than you have 1s. Every 2 would have been bumped up by a 1. And so now when you put a 2 here or a 1 here, it comes to rest in the same place, right. So the way the shape, so now we are looking at Q of W. So you are looking at the way the shape is increasing. So until this point anyway there is no difference in the way, so W prime is U1V. Until this point there is no difference in the way the shapes are increasing. Remember, the recording tableau Q keeps track of how the shape changes each time you insert something, right. So you put, if that box was added at the ith stage, you put an I in Q. So until this point anyway there is no difference in the Qs. The only question is what happens at this point. At this point what happens is that you have in the P, you have a bunch of 1s and a bunch of 2s, and now you are inserting a 2, and it will come to rest here, and also the 1 would come to rest in the same place. So up to this stage again the Qs would be the same, and after this what happens is that you only have 2s after pairing of the 1s and 2s, and that will mean that so P of, so this is P of u, this is P of u2, and this is P of u1, just a 1 here and 2, 2, 2. And now after this, after you pair off the 1s and 2s, you are only left with 2s. So you may have that some 1s bump up 2s, but they will never be able to touch this 2. So again the shape thing will be the same. Okay, I probably didn't explain it very well. It's a slightly subtle point. As okay, so you just show this for each single crystal operator. So what this means is that all these words will have the same Q.
First word of, alphabet of V has to be a 2.
Yeah, it has to be a 2. So that will just come to rest on the right here. Yeah. And every time you have a 1, there would have been a 2 that has come before it. So if it bumps it up, it would bump a 2. It won't even touch this part always. It will, whatever happens will happen with the stuff that comes later. That's the key point. And when you have more letters, the proof is a little more complicated, but this is the basic idea behind the proof. So yeah, bit. The other important point feature of these things is that is that if the second main result is that if W is congruent to W prime, then HW is congruent to HW prime for H any of these. Okay, so the point is you only need to prove these for EI and FI. Sigma is some power of EI or FI. And so what this is saying is that if you apply a crystal operator to a word and then look at its, so if you take a word and take its insertion tableau, you apply a crystal operator and take that insertion tableau, then those two insertion tableaus will also differ by the same crystal operator. So this one, the proof as you could guess is just to check it for one Knuth move. So enough to check for a single Knuth move. So let us look at a Knuth move of the form u y x z w and v, and so this is my w, and let us look at w prime equals u y z x v, and what is the condition here on x, y and z? Is that the one or is it the other one? Okay. So now we are going to apply, let us say we apply operator EI to both these. So we will have EIW and EIW prime. So now there are various possibilities. We could be looking at something like, okay, so if I or I plus 1 is not any of these letters x, y or z, then there is no problem because it does not even affect this part and it just operates on these parts, and so these parts are actually equal, the same Knuth move applies on those. So the only issue is when when I or I plus 1 comes from the letters x, y and z. So you just have to work out a few cases, and I will just do a couple of these cases. So let us just look at the case where okay, so suppose we have, let us look at the case where we have u I so it could be that x is I, y is j, and z is maybe something else, and we have v, right? And it could in fact even be the case that this is the place, this is the crucial, the magic place where the I gets changed to a j, and so what we have is maybe EIW is u, and then I I Z V, right. It could be this could be one of the cases. Then what is W prime? Then W prime is U I Z J V. Oh, okay, I should take J I Z, right? Yeah. Okay, so if it's J I, then it doesn't matter. They'll be yeah. Okay, so yeah, I can't take this. So let's take so y. So let's take x z, right? So y I j, and this would be y j I, and here we'd have y I, and here we'd have u y. This so yeah, so this is a bit confusing, because now what happens is this j I may get so this so up till here everything is cancelled out. So this j I may get cancelled out and the thing may move to another place. Let's just do a simpler case. So where I have x I z, y I z, and this I is changed to a z j. Maybe next time I'll prepare more carefully. Y j z. So y I z, that changes to y j z, and this changes to z I, this changes to z j, for example. So then what happens here? So these two are Knuth equivalent. Huh? Oh, sorry, I've swapped the Knuth and these things. Z I, y j z, and y z j. That's still okay. So question is, are these two Knuth equivalent, right? And so what has happened is that this j, this I has been replaced by a j, but it's implicit here that the j is not equal to z. In that case, these are still Knuth equivalent. Okay, so there are a bunch of other cases which I need to do carefully, but I think I'm running out of time, so maybe we'll do it either in the tutorial or tomorrow. I'll just finish these cases. It's yeah, it's sort of it's given in this LLT book. So that's the second fact about that. If two words are Knuth equivalent, you apply the same crystal operator to them, then the result is again Knuth equivalent. Okay, I'll stop with this. Even if j is equal to y, then sorry, j is equal to y. So yeah, we could have no, but j could be equal to y. That's true. Yeah. So then that's still, then it's not clear, right? Okay, let's stop this.